So now based on that we will start with that diode, how this diode they are exactly going to work. So now what we have to do for the formation of your diode, you have to take a p-type semiconductor likewise and another is n-type semiconductor, then they just join together. So in p-type semiconductor the majority of carriers are holes, in n-type semiconductor the majority of carriers are that is electrons. So now what will happen, so when I just join them, okay, so definitely the same thing which we have just discussed over here. So that is how it consists of different your mobile holes, immobile negative ions, so which we have just seen over here. Now the next thing, based on that what will happen after the formation. So in short also I can just tell you over here. So when they are just connected, so this is the boundary which connects it. So when I join that, yeah, obviously that n-type semiconductor consists of large number of free electrons. So the just free electrons will move towards this p-type. So there is a vacancy he can see in the p-type. So immediately he jump over there. Yeah, so this n-type semiconductor loses one of the electron. So there is a formation of your positive ion which forms over there, which is the immobile ion. So at the same time there is a negative ion on this p side, which are again immobile negative ions. So there is a formation of immobile ions, positive and negative ions. So that will create the electric field. So that will create the electric field, and at the same time you can say that this region is nothing but the depleted of free charges. Now there are no free charges are available within that certain boundary of junction of that your diode. So this is called as a depletion region. So this one you can call it as a depletion region. So that is a depleted of free charge carriers, and at the same time there is some barrier. So some potential barrier has been created. Yeah, so over there, so that is also what we can call as a potential barrier. Yeah, so the same thing now which I had just shown, initially they can come, but after that, so definitely they can't enter into another region. So now based on that, so what is your forward bias? Now first of all, what do you mean by biasing? So biasing means you have to apply some external voltage to that your diode, so which mainly consists of your p and n junction diode, which we are going to connect over here. Yeah, so that is your diode. Now what will happen, how it exactly behaves when I just apply some potential across it. So in forward bias diode, so definitely you have to just apply the positive terminal to your p type and the negative terminal to the n type. So you can see that, so when you just do that, so the electron from this negative terminal, yeah, so obviously they just enter over here, and at the same time, so they just push this electron onto this your, that is a junction side. Yeah, and definitely this region, the depletion region starts decreasing, the width of that depletion region starts decreasing. Yeah, and finally a large number of free carriers, those nothing but electrons, so it can passes through this, and they finally just came out from this your positive terminal. So this is how the flow of current will take place in case of your forward bias. Yeah, so simple again. So in case of your n type, there are large number of free electrons, so there is a negative, you can say that, potential over here. So all the free electrons are forced to move on the left side. So there is obviously this depletion region, so there are this positive ions. Yeah, so this gets filled over here. Once they get filled, obviously the electron has been pushed on the left. Yeah, and at the same time there are holes also, so they will just enter into that hole, and at the same time they just came out through this another end, and this is how the current is going to flow through this forward bias. So in forward bias we are making sure connect the p type semiconductor to the positive terminal of external battery, and this negative terminal to the n type of semiconductor. So this is what we can call as a forward bias. The same thing we can show over here also. So this is how it looks like, that is flow of your current. Yeah, then that is the same thing which we had just discussed. Now we will see the next case, that is the reverse bias. So in case of reverse bias, obviously you have to just change the polarity, connect the negative terminal of battery towards the p type semiconductor and positive terminal towards the n type. So what will happen now? Because of that, now you can see that the width of depletion region starts increasing. Yeah, so this is how we can say that initially the depletion region was. Now after connecting it, so let's say this is how we have connected. So you can see that the holes and electrons, they just move away. So since this is positive and this is negative, so they just move away from that your depletion region. So obviously the width of depletion region goes on increasing. Yeah, so definitely the potential, that your barrier potential also you can say that that has been increased for this case. So this is how we can say that. So the reverse bias. Yeah, so mainly this is the depletion region, so its width has been increased and a very small minority current that is flowing over here for this reverse bias. Now at the same time the majority carriers are pulled away from the junction that we have discussed. Yeah, so this is again the diode characteristics. So how we will just discuss that diode characteristics over here. So that is, one is the forward bias. So you can say that up to this region there is no flow of current, so that is a non-linear region. Even if I increase the value of your voltage, yeah, but still the current is 0. That is why, because in forward bias obviously there is some barrier potential that we just mentioned and it is around 0.2 to 0.7. yeah, so for germanium it is for 0.2 to 0.3 and for silicon it is 0.7 volt. Yeah, so that external potential has to overcome first that barrier potential, and then the voltage and current, they are in proportion with each other. So then after that I am just showing this region which we are going to call it as a linear region. Yeah, so we can say that the current is in proportion with the voltage in the linear region. Now if you just change the polarity and you make it in the reverse bias, so you can say that the value of current is almost 0 up to certain instant, but once the breakdown occurs, that breakdown voltage, so definitely a large amount of current will flow. So that is called as a breakdown condition. So this Vk is called as a knee voltage. Yeah, so you can show over here also. So this cut-in voltage or knee voltage. Yeah, and then this Vb is that we call as a breakdown voltage. So after that suddenly a large amount of current starts to flow. So that is what we will call as a breakdown voltage for this particular case. Yeah, so the same thing you can measure, or you can do the experiment by measuring the voltage and current by just increasing that here voltage over here.